Right, I think we can get started now. Maybe a few more people will chime in, but we should not lose more time. So hi everyone, that's my pleasure to welcome you to this new Clever Planet seminar for the Spring 2022 seminar series. Today we have Dr. Christoph Burkhardt from University of Münster to give a seminar, and we're really excited about that. As usual, we'll start this seminar by me saying a few words about the Clever Planet project, as well as giving an acknowledgement before introducing the speaker a bit more. So let's go with that. Okay, so the Clever Planet project is a multi-institutional, interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it is supported by NASA. It is also one of the teams of the Nexus Exoplanetary Science System Coordination Network and the astrobiology. And here at Rice University, our research is pursued on the traditional land of several native people, namely the Karankawas and Sanas, as well as the Cohahuiltecan, represented today by the Tapilam Cohahuiltecan Nation, and the Ishaks, represented today by the Atakapa Ishat Nation. We see as our duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. So now a few more words about our speaker for today, Dr. Christoph Burkhardt. So Christoph got his diploma, got actually two of them from University of Cologne, one on petrology of silicate inclusion in IB iron meteorites, and one on the hafnium tungsten system in calcium aluminum rich inclusions. So for those who don't know, diploma is the equivalent of the master's in the American system. He then moved to ETH Zurich, where he got his PhD on molybdenum isotopes and solar system evolution in 2012, PhD for which he received the ETH Outstanding Thesis Award. He was then a postdoc for 6 months at ETH before crossing the oceans, joining University of Chicago for 2 years, where he was postdoc as well as lab manager until 2015. Then he went back to Europe, where he was postdoc in University of Münster for 2 more years before getting a permanent position as a research assistant, where he is since 2017. And today, as you can read on the title of his talk, will be the mode of terrestrial planet formation and heritage of Earth is volatile, the story from isotope anomaly in meteorites. So with that, Christoph, the floor is yours.
Okay, thank you. I guess I share the screen. This one. Okay. Yeah, thank you very much, Maxime, for the intro and that I'm allowed to speak here. And I'm going to present you some of the work I did in the last years. And I'm trying to present you what isotopes in meteorites can tell us about how Earth formed, and a little bit maybe also on the heritage of Earth's volatiles. So spoiler alert, this heritage of Earth's volatiles, this, I guess most of this is coming in the next talk at one point. So today I will pose a few questions that I try to answer with isotopes. The first is, what is Earth actually made of? And you will see that this will lead to an even more fundamental question, which is how did Earth actually form? And then I will quickly touch on a question that in some of your minds might be popping up now. This is, why should we actually care? And then lastly, I will say a word about what all of this might tell us about the heritage of volatiles on Earth. But if we start with like, how did the Earth form? You might say, well, this is more or less textbook knowledge. Planets or terrestrial planets are a byproduct of star formation, and stars formed by the collapse of molecular cloud cores, and due to angular momentum conservation, we get some accretion disks of gas and dust, like the one here of HL tau, and inside these disks we have dust, and this dust can coagulate and may be added by a streaming instability. We end up with some planetesimals, and these planetesimals then collide, and runaway accretion grows, get to planetary embryos. These planetary embryos can collide long after the gas disk is gone, and until then we end up with something like the terrestrial planets. And I think we had a good idea that we understood some basics of these processes at least. And we thought, okay, we can model it, like in this model here from Sean Raymond. We have some distributions of planetesimals and embryos, and we hit the go button. And they collide and they grow to bigger bodies. And this is in millions, tens of millions of years time scale. And in the interest of time here, I will skip this to the last screenshot. So what we end up with is some kind of terrestrial planets, and even something that resembles maybe the remains of the asteroid belt. So we had thought a pretty good idea of how this might have worked. The point is, as you see here, there's also already some Jupiter analog, and this is there from the beginning. That means there must have been something there before all these terrestrial planets formed. And the idea for getting the gas giants forming fast is that they formed outside of the ice line or at the ice line, and there's more condensable matter beyond the snow line or the ice line here. That means there's more stuff that can form maybe an embryo, and there's larger embryos, beyond the ice line. And if you have a large embryo to start with, then maybe another accretion scenario can happen. And this is the pebble accretion. And it basically says that you settle small particles on a large body in a gas disk. And that depends on multiple parameters, but the larger the body that you have, the more you can also assemble onto it. And this was put forward as a way to explain why the gas giant planets were there relatively early, so that their cores formed by pebble accretion. And then people said, well, this is a good way to make the giant planets, or the cores of the giant planets fast. So this is just another animation that shows a pebble is accreted while a planetesimal is just deflected, and so you can get a lot of mass quickly onto these embryos. People have thought, well, if this works for the giant planets, maybe we can do the terrestrial planets also by pebble accretion. And there have been a couple of papers now that showed that, well, it is actually possible. Maybe we formed the terrestrial planets also by pebble accretion. So we are basically left with a relatively unconstrained mode of terrestrial planet formation in our solar system. So we can have either maybe pebble accretion, where we have built the terrestrial planets within the lifetime more or less of the gas disk, so within 5 million years, or we have the classic model where we grow first planetesimals and then the embryos from local planetesimals, and then they grow over tens of millions of years into the terrestrial planets. So this is a pretty different time scale and a different process. And unfortunately, from isotope age dating, we cannot really tell a difference, or we cannot distinguish that. But what the models tell us, well, what is distinguishing is the outer solar system input. So if we have pebble accretion, that means we have a large flux of pebbles drifting in that end up on this planet. That means we will have a lot of stuff coming from outside that is drifting inwards that ends up on this planet, if this is a viable mechanism to grow them. While in the classical model, we have a rather limited solar system input, outer solar system input. So this might be a way to distinguish those. And in a comic world model, this looks like this. So we have the classic accretion model where we have local embryos from local planetesimals. These are in red inner solar system stuff. And then we have just a bit of blue stuff coming from outside, maybe the movement or just the Jupiter being present that scatters this stuff inside. And like what the models show us or give us is that there's a few percent of this stuff ending up in the terrestrial planets. While in the pebble accretion, we have like the embryo core of red stuff, and then in the disk, while the disk is there, there's a lot of stuff coming from outside, moving towards the sun and ending up on the terrestrial planets. So the models gave us 50% or more of outer solar system dust being finally in the planets. So to distinguish then these models, we need to see how much blue stuff is actually in the Earth. And we can do this with isotopes. And since many here in the audience are not isotope geochemists, I will do a very brief intro. And isotope variations basically can come in two different flavors. They can be mass dependent. This is fractionation that happens during chemical reaction or isochemical reaction, crystallization, condensation. And with those, we can look into processes. So we can see what conditions certain processes happened at what conditions, so which temperatures or so. And then there's a second family of isotope variation. This is mass independent variations that could be due to radioactive decay that gives us ages, or that could be through nucleosynthetic anomalies or cosmic ray exposure, which is not dependent on the mass of the isotopes. And this can be used as tracers. And these mass-dependent isotope variations are usually given the delta notation. And this is the notation of an isotope ratio in a sample relative to that of a standard in parts per 1,000, so in per mil. And we have here a sample A that is fractionated relative to a standard, which would be at 0. And the light isotopes are enriched and the heavy isotopes are depleted. And this sample has a mass-dependent fractionation, but it does not have a mass-independent isotope variation. And this mass-independent data is usually given in epsilon notation. And this is not just adding a digit to the exponent here, because what you do is you take this measurement and you take any two isotopes, this one, and you say, whatever this difference from the standard, we assume this is mass-dependent fractionation, and then you correct those back to 0 in doing it's an internal normalization. So this is in this beta factor, and you do this for 2, and then you correct all the other isotope ratios the same way, and that brings to you correct basically for any mass-dependent fractionation that might have happened to that sample during measurement and in nature. And then this sample has no anomaly. So a different is the next sample here, it's mass fractionated here, but then there's deviations from the mass-dependent fractionation. And if we then do the internal normalization, you end up with an anomaly here that would be maybe burnout due to cosmic ray exposure. And maybe this excess here would be due to radioactive decay, like a daughter product that accumulates. Okay, So it's just important to note that you can do different things with mass-dependent and mass-independent isotope variations. And we will use mass-independent variations because they are really a great tracer. And if you come from geochemistry, then maybe these diagrams are familiar to you. So this is an example of how you can use mass-independent anomalies as a tracer. This is just looking at different MORB samples from all over the world. And you can then, they retain basically a signature of their mantle source. And then you can see what kind of different reservoirs are in the mantle present. And we do the same thing now, but not for the Earth's mantle. But we look at isotope anomalies in meteorites to see what kind of reservoirs are in the solar system. And we do this with meteorites, and they come in two flavors. They're undifferentiated meteorites and they're differentiated meteorites. So differentiated meteorites come from differentiated parent bodies. And this iron meteorite comes from the core of a differentiated small body. And undifferentiated meteorites, you can also think of them as space sediments. They're called chondrites. And there's non-equilibrium assemblages of all kinds of stuff that can be high temperature components like these CAIs, all the stuff in the solar system, and low temperature components like organics in the matrix. And this is really like the stuff that was around in the disk at the time these bodies formed. And in this matrix, we can find some small grains with huge isotopic anomalies. They're called presolar grains. They have isotopic anomalies that are largely different from anything that we have on Earth. Like, for example, this grain is super enriched in 28 silicon, so it's nothing of the other silicon isotopes. And these are grains that formed in nucleosynthetic processes in previous star generations. So from studying these in meteorites, we know that the parent molecular cloud that made our solar system contained materials from previous star generations, like from AGB stars or from supernova or kilonova explosions. And this stuff made it into our parental solar system's parental molecular cloud, and there into the disk. And either directly those grains or stuff that is forming from them at one point was at one point heterogeneously distributed in the disk, such that bodies that formed at different places in the disk or at different times had slightly different isotopic compositions. So that means stuff that maybe formed further out had more blue instead of red, and stuff that formed further in had more red instead of blue. And this is actually what we see in meteorites. So if we take bulk meteorites, then they fall in one of those two clusters here. It can be either the CC meteorites or the NC meteorites. So that's all stuff that's coming from the asteroid belt, but they are falling in two isotopically distinct clusters. And this is independent of whether they're differentiated or undifferentiated. So both of these clusters contain differentiated and undifferentiated meteorites often. And this is for chromium, titanium, the classic Warren plot. But this is also for other elements like molybdenum. We also have the same dichotomy. You have these red parent bodies and these bluish parent bodies. So there's a fundamental isotopic dichotomy among the meteorites. That means there's two reservoirs present in the asteroid belt now, but they formed elsewhere. So how did this dichotomy form? Our idea, well, I'm not alone there, there's other people that proposed this as well, is that this is inherited from the infall stage of the disk. So that means the first infall that there was more bluish, let's say, and this is like sampled by what the CIs, these calcium-aluminum-rich inclusions today, show in isotopes. So these formed early, close to the sun, and this is at the stage where the disk is only forming. And then the infall was this bluish stuff. Then we have outward transport of this, and actually the disk actually forming and spreading outward. And then you change to more reddish stuff that falls in. And in the outside, you have this blue retaining. And then with time, in the inner disk is dominated by the red stuff, while there's still some blue outside. So, and then infall is done, and then you have outside more blue and inside more red. And then the idea is you form the CC bodies in here, and the NC bodies further in, and the CC bodies further out. And this is obviously a very simplified model, but it explains quite a lot of the observables in the meteorite record. So there's excess CIs out here, more unprocessed dust, it's more volatile rich, and it has a CC composition, and inside you have more highly processed stuff, a bit more volatile poor, and the DNC composition. So the whole thing may or may not have been separated by Jupiter. The question now, coming back to our initial questions, how much blue stuff is in the Earth? Then people went to these diagrams and said, okay, we just look, where does Earth plot in these diagrams? And this is the bulk silicate Earth here. And then they said, well, okay, I take the ruler and put it on here. And then I read off, okay, it's on the end of this NC trend towards the C meteorites. That means there's about 40% CC or outer solar system material in the Earth. And they use this to argue, well, this speaks for pebble accretion of the Earth or the terrestrial planets. The problem is, well, other people have said, well, maybe this is not the starting point. We have NC-type chondrites. They're isotopically very similar to the Earth. If this is our starting material, then we need less than 5% of outer solar system to make the Earth. And I would say, well, things are even more complicated, because from molybdenum, this is the NC bodies, the CC bodies, and this is bulk silicate Earth. No matter what you mix here of NC and CC, you will not end up at bulk silicate Earth position. That means if there's CC bodies made it to the Earth, then there's also stuff further down here that is unsampled actually by meteorites. So that is unsampled in our collection. So there's really a fundamental problem with the previous use of these anomalies, and to infer how much CC stuff is in the Earth. And the aim of the study that I'm presenting is that we wanted to sort this out. And the approach that we took is that we just did not look at single anomalies only. We looked at all the anomalies in multi-elemental space, and we tried to constrain composition and the origin of this unsampled component and see if there are trends that help us to constrain how much CC material is there. And obviously it's good when you want to talk about terrestrial planet formation, not to use only one. So we also added some data from Mars. And these are results. So again, chromium composition, titanium isotope composition, the plot that you've seen before. And now here is Mars, here's the Earth, and you can say, okay, this is a mixture between something here and up here. But if you go in other isotope spaces, this does not work. So this is zirconium versus molybdenum anomalies. And there, the Earth is an end member. It has an end member isotopic composition. That means if any of those things made it into the Earth, then there's also something missing further down the line here. And then what we did is we just changed the axis here, plotted chromium, molybdenum, titanium, zirconium, and you see this linear relation in this NC trend remains. and this is now pointing away from the CC bodies. So they are shifted from this NC correlation line. And Earth and Mars always plot on or very close to these correlation lines and not towards the CC composition. So you would imagine that if there's a lot of CC material inside Earth, then Earth would plot towards the CC bodies. And this is not what we observe. And again, we observe this correlation of these NC bodies. The Earth is on, and it has an end member composition. It means if anything of this made it into the Earth, then there must be some balancing stuff further up here. And this is true for all kinds of elements that you look at. All the NCs are correlated. The Earth and Mars plot on or very close on this NC trend, and this is not towards the CC bodies. They are shifted from the NC. So just by looking at that, it's already clear there's not much CC material in Earth, and the Earth and Mars, they're governed by mixing along these lines. So the composition of Earth and Mars is governed by two component mixing among inner solar system materials. And there's only a limited CC contribution. But now the point is there is some CC contribution because the bulk silicate Earth and bulk silicate Mars, they plot in between this NC and CC line in molybdenum isotope space. Now it's important to note that the bulk silicate Earth today, the molybdenum in there, is not representing all of the accretion history of the Earth, only the last few percent. This is because most of the molybdenum in the Earth today, in the Earth's mantle, is late, and all the early molybdenum there is gone to the core. So by looking at that, we cannot directly infer how much CC over NC material is in the Earth. It can only give us some insight that relatively late, there was some CC material added to the Earth and also Mars. But this gives us a starting point. So we have, if any CC material is in the Earth, which it looks because the Earth and Mars are elevated from the NC line, then there must have been some NC material down here that also made it into the Earth. So this gives us a model to start with. We say the molybdenum in the Earth, in the bulk Earth or Mars, is a mixture of some NC material that arrived late, some NC material that arrived early, which we don't have any idea where this plots on that line, and some CC material up here. And we can then cast this in equations that also involves the isotopes. And that leaves us with 5 unknowns. That is the isotope composition of the molybdenum isotope composition of the NC late component, the 94 of the NC early, the fraction of molybdenum in the NC late, the fraction of bulk CC, this is what we want in the end, and the fraction of bulk NC late. And just by looking at this plot, 2 of those unknowns can be read off. This is isotopic composition of the NC late, that would be something down here. And the fraction of molybdenum NC late, this is the length of this arrow relative to the total. And with this, we can now go, because we showed this, we can now go to non-siderophile elements and to use this correlation of molybdenum with chromium or molybdenum with zirconium to find out the bulk CC fraction, because these have the same functional form, these correlations, but different coefficients. But if we take 2 of those, then we can make them linear dependent or equivalent to each other for exactly 1 F bulk CC. And this is what we get from here. And we did this in the Monte Carlo way, where we varied all the arrows and the slopes of these correlations and so on. And the result that we get is here, the probability for Earth and Mars. The amount of CC material in Earth and Mars peaks at about 4%. So there's a bit of CC stuff in Earth and Mars, but not much. And that brings us back to the question that we ask. So for the classic model, we had a few percent, and for the pebble accretion model, the prediction was 50%. So from our analysis, we can stick with the classical model, and pebble accretion probably is not a viable model for creating the terrestrial planets in our solar system. Okay, this does not mean that I say terrestrial planet is not happening or is not working. Pebble accretion. It's just pebble accretion does not seem to be the dominant accretion mechanism for making the terrestrial planets in our solar system. Okay, so to sum this up, what is the Earth made of? We have found that it's mostly inner solar system material, some of it lost, we don't have that in our meteorite collections, and some whiffs of CC material, some few percent. How did the Earth form? Well, from this we can find that the classic accretion model, where we have local embryos forming from local planetesimals, is a better fit than pebble accretion, which may mean that the pebbles did not make it to the terrestrial planet formation region because this was sheltered by Jupiter that just sucked everything up that came in. Now, why should we care what the Earth is made of? Well, we should care, well, as geochemists at least, or geoscientists, because like the ruling paradigm is that the bulk Earth composition can be approximated by chondrites. So at least for refractory elements. And this is like the basis for inferring the timing on conditions of Earth differentiation, for example, using the samarium, neodymium, or lutetium, hafnium chronometers. So they are referenced to CHR, which means chondritic uniform reservoir. And we use this to infer the timing of crustal extraction from the mantle. And therefore, it was quite a surprise when Boyer and Carlson found that the 142 neodymium of chondrites is different from that of modern terrestrial mantle-derived rocks. That means if chondrites are representative of the bulk Earth, then, and this is what the mantle is today, then there must be some reservoir that is balancing this on the other side. And that was proposed that this is an early enriched reservoir that's full of incompatible elements that must have formed very, very early in Earth's history. And then it was proposed, okay, that might have been lost to space by impact erosion, or it might be hiding somewhere in the mantle. This is what geochemists do when they need to make sense, they invent a hidden reservoir. But what we have seen previously is that for some isotope variations, the Earth is an end member. So what we figured out is that this difference is real, but it's not related to the decay of, say, 146 samarium. So this is not a radiogenic signature. This signature is nucleosynthetic in origin. So because the 142 anomaly correlates, which is also the radiogenic isotope, correlates with the 150 neodymium, which is non-radiogenic, and that correlates in a way that is indicative of nucleosynthetic variation. So for Earth, we have neither a hidden or lost reservoir. It's just that we cannot blindly take the isotopic composition of chondrites as being representative for the Earth. So, and knowing that is obviously important if you want to get the correct geologic history of Earth. Okay, so then why should we care? Well, the knowledge of the building blocks is really the prerequisite for correctly interpreting Earth's evolution. And now the last point I want to make here already. What does this all tell us about the heritage of Earth's volatiles? And I guess this is what you are working on a lot. And I have to say, so far, maybe this does not tell us too much. Well, what did we find out? We found out that there's a few percent CC or other solar system material in Earth. But this is for the bulk Earth, and this is we found this out with refractory elements. So a few percent of the bulk Earth is from the CC reservoir, but this does not tell us how much of Earth's volatiles actually come from there. Obviously, if we think there's a few percent, and we think this is volatile rich, really carbonaceous chondrites, CR1-like material, then this is more than enough to explain all of Earth and Mars volatiles. So these few percent could, in principle, tell us, could all come, if they are CC, this could bring all the water and so on that we need. The question is, we don't know if this is true. So what we cannot tell right now is we can't differentiate between the wet or dry accretion. It could be that the Earth accreted wet, or there was a lot of volatiles already in the inner solar system. And then the few percent CC material that was added was maybe not that wet as C1 carbonaceous chondrites. It might have been also drier. Or it could be that the Earth really accreted bone dry, and then some wet, really wet CC material did bring all the volatiles of Earth. But we cannot, based on what I showed you before, so from these refractory elements, we cannot differentiate between that. So what we need is really the fraction of CC that in volatiles. And for that, we need data from volatile elements. And now the problem is the volatile elements that we have, for example, hydrogen, carbon, nitrogen, that you're working a lot with. In terms of isotope geochemistry, for me, they're not that useful. I don't want to step on anyone's toes here, but they have only two isotopes. That means we cannot do this internal normalization. We cannot differentiate between process and source signature. And therefore, it's a bit ambiguous, let's say, at least. And traditionally, the isotope composition of Earth in these elements has been linked to an addition of volatiles from CC, the carbonaceous chondrite region. And this is shown here for hydrogen isotopic composition. This is a range of carbonaceous bodies. And this is Earth's ocean and Earth's mantle. And this overlaps for sure. But in a paper in 2020, Norette Piani, she showed that actually in ansatite chondrites, this is the composition of ansatite chondrites. First, the isotopic composition, and second, that these ansatite chondrites contain more OH or water than we actually previously thought. That if that opened the possibility that a lot of Earth's water might actually come from ansatite chondrite or inner solar system like material. But we cannot really differentiate because there's only two isotopes then. And then this is work from your group here, from Creval et al. In Nature Astronomy. They linked nitrogen isotopic composition with the NC-CC difference that we have from refractory elements for iron meteorites, and they showed that NC iron meteorites, so from the inner solar system bodies, they tend to have a isotope composition that is lighter compared to the CC meteorites. And Earth is somewhere in between, but again, there's a bit of overlap. So there's an indication I mean, if Earth's nitrogen would be here, then it would be clear. But so we don't know for sure, but it could be that Earth sourced stuff from both of these regions. If we go to oxygen, then this has 3 isotopes. That's great. We can look for anomalies, and there are a lot of anomalies in oxygen. But oxygen is not only volatile, it also forms refractory oxides. Yeah, so it's not entirely a volatile element, let's say. And it's also ambiguous because this is the terrestrial fractionation line, so everything on Earth plots on that line, and there's carbonaceous material above that line and below that line. And there's NC material, like ordinary chondrites, above this line, and there's NC bodies below this line. So it does not really allow to differentiate where Earth's oxygen came from. There was a recent study on krypton isotopes that also has enough isotopes, but to me this is also a bit ambiguous. So they found that primitive krypton from Earth's mantle tends towards a composition of carbonaceous meteorites. So, and they then said that Earth's krypton accreted relatively early within the main phase of accretion, and that from a more or less chondritic source. But what we have here is we don't know where NC meteorites plot, and there's actually, I think, the overlap. So this is not really, can us give the right answer yet, I would say. So what we would need, my ideal world would be that we need some volatile element that has 4 or more isotopes, and that we can measure in differentiated and in undifferentiated meteorites, and that show a clear NC and CC distinction. And then we can see where does Earth plot relative to those. If Earth plots in here, then it means all of the volatiles are more or less from CC, which means it was more dry accretion and all the stuff came from CC. While if it plots in the middle, then it means it got volatiles from both sources. And when it plots here, it means that it was more or less a wet accretion, and most of the volatiles come from the inner solar system. And I think the good news is we might have such a system identified. The bad news is I cannot tell you right at the moment. This is ongoing work. So I'll leave it here. The conclusions again: Earth is mainly made out of inner solar system material. How did Earth form? Probably not by pebble accretion. Obviously, it's important to know what Earth is made of, because if we want to correctly interpret Earth's evolution and the heritage of volatiles, I think it's still an open question, but progress on many fronts is on the way. And with that, I will stop here, and I'm happy to take questions.
Great, thank you very much, Christoph. It was very interesting. So now, if you have questions, please put them either in the Q&A, or if you want to speak up, raise your virtual hand, and I'll make sure you can speak. So I think we already have one question in the Q&A. Martin Schecker says, very interesting work and interpretation. My question concerns the planetesimal versus pebble accretion scenarios. Do you see any observables for exoplanet systems to get an independent constraint?
Yeah, obviously that's an interesting question, because this pebble accretion model might be very applicable to exoplanets, and it also might happen there. I'm not the observer that I'm know that, I mean, I'm sure people have claimed that there are some planets forming by pebble accretion and some exoplanets forming by that. And I'm sure that they are forming by this process. And I think there was a paper today or so in Nature Astronomy, like the first detection of a giant planet pretty far out, and they thought this might be core accretion, but some people are not convinced, and it might be still some pebble accretion might play a role. So this is an active debate, I would say. From what we showed is that in our solar system, it may not be the dominant process. Yeah.
Okay, I guess Martin wants to react to, so I'm gonna allow him to talk, because that should be.
Cool, yeah, thank you. No, yeah, that's a very interesting point there. The reason why I'm asking is so from all we saw about simulations of protoplanetary disks and how dust is evolving in there, we're pretty sure that pebble accretion is something that kind of has to happen, that you get these inwards drift of millimeter to centimeter sized particles. And then there's, of course, a lot of caveats regarding if this is the dominant mechanism to form our planets, as you have pointed out nicely. And so, yeah, I'm just super curious if there's something, some observable maybe on population level trends in the exoplanet population. We now have 5,000 exoplanets discovered that we can use to better constrain these different things. Is there a, let's say a bulk parameter that one can measure? Do you, for example, predict a different bulk density of a planet if it has accreted these volatiles from outside of the system as opposed to only inner material? You know, these would be the kind of helpful observables that we could look up.
Well, I mean, again, I think Jupiter or Jupiter's core, certainly there was pebble accretion involved. And when we compare our solar systems to exosolar systems, or the ones that we know of, then we see that our solar system is relatively special in that it has Jupiter at its location where it is, and it has no super Earths or mini Neptune planets further in, as many of the exosolar systems have. And that might be an indication that Jupiter was there and sheltered the terrestrial planet formation region from the stuff that was coming in. And if that would have not been so efficiently done, then the Earth might have been a super Earth. Maybe this goes in the direction.
Yeah, that's super interesting. So maybe we should look rather for architectural trends of whole multi-planet systems. So, if you have an inner planet, is there a giant planet in there as well? And maybe that's helpful then. Okay. Interesting.
Yeah, in the end, there's a lot of chaos happening. If
that's for sure.
In or out, but I guess going through the populations and look for architectural trend might be an indication. Yeah.
Okay, cool. Thank you.
Right, then we have a question by Francis Nemo. It seems natural to assume that the about 5% CC was delivered late in the accretion sequence. Is there any actual evidence for that?
Well, we see it still in the molybdenum. If that would have accreted very early, it would not be visible. Like if it would, then after that only NC stuff would have come in, then all the signature in molybdenum would be gone, and for molybdenum the Earth would be on the NC line. But and like from the modeling or from the dynamical models, when Jupiter was there to scatter stuff in, that was still when a disk, a gas disk was around, or if Jupiter moved in or out, then that would have happened relatively early. The question is, well, this stuff from outside made it to the inside, and then it made it to other bodies, and that it could be that, like the embryos that then collided at one point in Earth's history, that they had this mixed signature, and that got inherited by Earth and Mars. So I think the timing of when that scattering of this CC material inward happened is relatively early, but then the bodies that were forming from this stuff then through embryo collisions, that they already had this mixed signature. Maybe it's that way, yeah.
Right, then we have another question by Tom McColomo, who asks, how are bulk isotope values for bulk Earth determined, and what are the uncertainties for those values?
Yeah, so bulk means we take a piece of the meteorite, and we hope that's representative, and then dissolve it and measure it. So this is how it is determined. But if we take a chondrite that has, let's say, is relatively coarse-grained and has different components, then if you manage to get a CI in that has a very different isotopic composition from the rest, that will influence your bulk measurements. And that means for the carbonaceous chondrites, I think all the data that is out there, there's some variability due to different amounts of CI sampled in different studies. But overall, the spread is getting less, let's say.
So I think I might have misread the question. The question was about the bulk Earth values.
The bulk Earth value. Yeah. Well, this is what we take chondrites with for usually, and this is like also a very good first approximation, and it's just for the isotopes. This is what I showed. Because there are isotope variations among different chondrites, then it's difficult to take any of those to represent the Earth. So we know now none of the chondrites represents the Earth for the isotopes, but it depends on the system you look at. And they nevertheless, for the chemical composition, I think chondrites are still very good first approximation for refractory elements, at least. Yeah.
Right. Do we have other questions? Please, if you do.
Yeah. Quick follow-up, I guess, Christoph, on Tom's question. What he may be asking is, when you are plotting the bulk or the Earth value in all these plots, what are you actually measuring?
Okay.
I think that's what he's.
Yeah. No, we obviously measure the bulk silicate Earth is because we don't have samples from the core. So, and this is measured from mantle-derived rocks, and because we are looking at anomalies, so any mass-dependent fractionation also should not matter. So, and everything, the mantle should have a homogeneous composition for most of the stuff. And depending on the elements we look at, if we look at zirconium or titanium, which is a lithophile element, so any rock on Earth that we should take should have the same isotopic composition in terms of mass independent variation. So, and this represents then the bulk silicate Earth, and because it's a lithophile element, that also represents the bulk Earth. For molybdenum, if we take a sample from wherever on the crust or the mantle, then this represents the mantle, the current mantle. And this is not the bulk Earth, this is the bulk silicate Earth. This is what I said. And depending which element you look at, you sample different phases of accretion. So a siderophile element like molybdenum, the bulk silicate earth value is the today's value. And during accretion, that might have been different, but all that stuff is now in the core. So we sampled the current day bulk silicate earth, and depending on the geochemical character of the element, that is the bulk earth, or integrating through all of accretion, or being biased toward later phases of accretion. Like a highly siderophile element, we only sample maybe the last 0.5% or last % of accretion, because everything else is in the core.
Yeah, thanks.
All right, thank you very much. I guess if we have no more questions, then we will close it here. And thanks, Christoph, again. It was very interesting. So thank you everyone for joining, and we'll see you in 2 weeks for the next Clever Planet seminar. Bye-bye, have a good day.